All right, welcome to another lesson. This is a Unit 1 lesson under Module 2, where we're going to speak on oscillations and waves, right? And we're going to talk about different types of waves, the characteristics of a wave. Those are some of the things that we are going to be discussing here. I want you to pay keen attention, take notes, remember to comment, asking questions if you don't understand something, right? So let's proceed. As you know, as from fifth form level, I think we should understand what is a wave, right? Right. Here we're seeing that whenever we're talking about wave motion, it's a means of which energies move from one point to another. So when you go to the beach and you're seeing those waves moving up and down in the water, right? It's really energy that is being transferred, all right, from one point to another point. Now, as it relates to waves, there are certain things that you'll hear us talking about at all times. One of which is what we call the displacement. Now, it says the displacement of a point on a wave is the distance from the center line, right, to some point. So here's our center line right here. This is the center line. It's almost like drawing a graph, obviously. That's our center line. Your displacement is that distance from the center line to some point. So if I were to find my displacement here, all I would do is to read it from my graph. So my graph is going up by, you know, 1 centimeter to every one unit. So clearly, based on this, this might be about 1.2 centimeters. So that would be my displacement. Now, another thing that you hear us talking about is the maximum displacement. The maximum displacement for any wave is what we call the amplitude, and that is measured from the central line or the center line, as we have indicated here, to where the wave stops. So right here, where the wave stops, is what we call the maximum displacement, and that's what we call the amplitude. Now, the amplitude can be in two directions. It can be in this position, and it can also be in the negative portion. So as you can see, it would be the same amount as we would have discussed earlier as being 1 point. This is going to be negative 1.2. And as you know, going down in this portion will be negative value. But that doesn't take away the fact that the amplitude is 1.2 centimeters. So that's your amplitude, maximum displacement. And on a wave, you will have several maximum amplitudes. At B is another amplitude. The only difference is that it's in the positive region here. Now, there are some other things that we need to talk about as it pertains to waves, and it's what we call a crest, right? Crest, as you can see here, it's the highest point, right, of the wave. So at Q1 right here, which is the highest point, right, in the positive region, that is what we call the crest. So always think about the crest being in the positive region. So at this point, we could look at A as well. A would also be a crest. If we're looking at Q1, that would also be a crest. If we're looking at B, that is also a crest. If we're looking at this position, it's also a crest, right? So that maximum displacement at all times at the top of the positive region, those are what we call crests. Now, when it comes on to the negative portions now, we don't call these crests, we call these troughs. So the lowest point, right, the lowest point is what we call troughs, right, troughs. So everything within this portion, you would call these troughs in a sense, but we generally specify that the lowest point is called the trough. Okay? So here's another trough right here. So remember now, in the positive region, those are what we call crests. And then now in the negative region, these ones are what we call troughs. All right? Those are what we call troughs. Now, one other thing that you must understand is that if we're considering this wave right here, that starts at 0 and going all the way over like this, right? and we have two locations here, P and Q. Because P and Q are on the same y-axis line, right? We say that they have the same displacement, and you could even measure it. So if you're measuring go all the way up, this is probably going to be 246. So it's going to be 0.2, 0.6 rather. And at Q, it will still be 0.6. So we say that that have the same displacement. At R as well, because R is on the same line, that same vertical line, then it also means that R has the same displacement as P and Q, and also with S as well. So all of those would have the same displacement. All right. So that's something to be mindful of when it comes on to points on a wave. If they have the same displacement, we say that well, if they're on the same point, they have the same displacement. All right. So that's basically some stuff that we need to be mindful of. Similarly, if we're considering A and Q1, they have the same displacement. So because they're on the same point, right? So that's pretty much a few things that we should be mindful of. So we have talked about the displacement just now. We talked about the amplitude, right? And as you know, the amplitude is the maximum displacement, and that can occur on the positive region and on the negative region of the graph. And also we talked about the crest. Crest is that highest point, which is basically your amplitude, right? So whenever you're on the positive portion, in the positive portion of the displacement, the highest point there would be the crest, the lowest point would be the trough. All right. Now, here we're now talking about the period T. So whenever we talk about the period, we use a capital T to represent period, right? Whenever we're talking about the frequency, we use a common F to talk about frequency. And whenever we're dealing with waves on a whole, period is not the first time we're hearing about period. Anything that oscillates will have a time period. Anything that oscillates will have a frequency, right? As you would have learned in simple harmonic motion, you know that period, right, is the time taken to complete one oscillation. Okay? So in this case, if you were to define the period, you would just say the time period of the wave, right, is the time taken to complete one oscillation from any point on the wave, right? So we're going to look at what we mean by one period very soon. And it says, what if now the points, right, on a wave makes n number of oscillations in t seconds? Then we can find the period by dividing the time, right, taken to complete those oscillations divided by the number of oscillations, as you can see here. So most times we are asked to find the period, which is just the time taken to complete one oscillation. But sometimes what we do is that we allow several oscillations to take place, right? As you can imagine, when you're trying to do a simple harmonic motion lab, you would probably count 20 oscillations, which is the time to go back and forth and all of that. And you obviously know the number of oscillations, so you just need to record that time, which will basically tell us. So if we divide up that now, we can find out the period of oscillation. That's what we mean. So you could say that, you know, for 20 oscillations, it took 20 seconds, for argument's sake. So then it means that to complete one oscillation, so if for 20 oscillations, right, so n is equal to 20, it took a time of 20 seconds. Then what this tells us is that T, capital T, which is the time period, right, to complete one oscillation would be the time taken, which is 20 seconds, divided by the number of oscillations, which is 20, which now tells us that the time period is going to be 1 second. So that would be the time taken to complete one oscillation. You might be wondering, what do we mean by one oscillation when it talks about waves? One oscillation can mean several things, right? It could be a case where you're starting from zero. So if you're starting from zero, then one oscillation is when we go, let me show you. So this is what one oscillation would be like. Right? So this right here, from where I moved a while ago, from zero, right? Completing this crest, and then I complete a trough, that will be recorded as one time period, right? There are other places we can calculate a time period from. We could calculate a time period from a crest to crest. So from here to here, if we were to measure that time from crest to crest, that would also tell us the time period. Okay? So just be mindful that to complete one time period, right? It would be from the starting, right? All the way back until you're almost starting a new crest. That is what we considered one period, right? So wherever you see a new crest that is going to be formed, then that is where you would consider to be your first period. Then now your second period would be that point again where another crest would be forming. So if you start at a crest, it means that you must end where the next crest starts to complete one time period. If you start if you start where the crest begins, I should say. So if you start where the crest begins, it means that where you stop is where the new crest is going to begin. Now we could look at it from the top of the crest. So if we were looking at it from the top of the crest, you want to measure the time taken from one crest to another crest. Good. We could also look at it from the trough. So from one trough to another trough, that would also be a time period. All right. As it relates to frequency. Now, frequency has to do with, the number of occurrence. So in this case, it says that the number of oscillations per unit time, right, would be our frequency. So if I want to know how many oscillations is occurring within 1 second, then what I would have to do is to find the number of oscillations and divide it by that time to find out the number of oscillations per unit second. So with all of that being said, we have come to this conclusion that says that our period obviously is equal to the time taken to complete those oscillations divided by the number of oscillations, whereas our frequency is equal to n divided by t. Now, we could transpose one of these, right, to make something becomes a subject. And then what you would see is that we could come up with a new lovely equation, right? We could come up with a new lovely equation that shows us that our period is the inverse of frequency, right? So let's see what's happening here. So if t is equal to, the period is equal to common t divided by n, right? And of course, frequency is equal to n divided by t. I could make, let's make t becomes the subject. If this t becomes the subject, then it means that period times n is equal to t. What I will do next is that I will substitute t into this equation. So if I sub t, common t I should say, I'm going to sub that t in that equation into f equals n divided by t. When I do that, this is not what I'm getting. I'm getting that f is equal to n divided by t times n. Then clearly I can see that n cancels n. Now leaving me to say that frequency f is equal to 1 divided by t. So having said all of this, now we see the relationship that occurs when it comes down to frequency and period. Frequency is the inverse of period, and period is the inverse of frequency. So from the period, you can simply know the frequency, right? So if I know the period, I must understand that my period is the inverse of my frequency, and that my frequency is the inverse of my period. So if I know the period, I can find the frequency. If I know the frequency, I can find the period. It's simple as that, right? And you will see this coming out in a lot of operations when we're doing stuff, all right? So just be mindful of that. Now, another key characteristic that we must talk about as it pertains to waves is what we call the wavelength, right? Is what we call the wavelength, and we should be able to what do you call it? Identify when there is a particular wavelength. All right, as you can see on my screen here, there are certain diagrams being shown right now, right? And for that reason, we're going to look at it to see where can we say a wavelength begins and all of that. There are several things you could consider. First, you could consider from crest to crest. So that distance from crest to crest, that would be a wavelength. All right. Now you could consider a wavelength from where this crest begins to where the next crest begins as well. So that would be your wavelength, and the symbol for wavelength is lambda, right? It's almost like a capital T, but it looks a wave. So this kind of look a little bit better as to what lambda looks like, right? So the length of one complete oscillation, and as you can imagine, one complete oscillation, as we would have told you before, is when we have one period. So remember, when we're looking at one period, we say that it would start from where the crest begins to where the next crest begins. It's the same thing when it comes down to wavelength. So whenever we're considering the wavelength, it's that distance that the wave travels to complete one oscillation. And it can be the distance between two consecutive or two successive peaks. So this is what we call the peaks as well. We can refer to it as the peaks, or we can say the crest. It can also be two consecutive troughs. All right. So from this trough to the next trough, right? So the distance between two successive troughs. Now, one of the most important things that we have to come to understand here is that whenever we complete one wavelength, right, is when two successive points are in phase and have a phase difference of 2 pi radians. So in order for us to consider a wavelength, firstly, we must note that the points must be in phase with each other. What I mean by in phase, they must be on the same level of displacement, right? So this point here is on the same level of displacement, so they are in phase with each other. But not only that, there will be a phase difference of 2 pi radians. So from here to here would be 2 pi radians. Now, one of the things that we must also understand, if this is one entire wavelength, then it means that half a wavelength is right here. So it therefore means that this now becomes pi radians. That becomes pi radians. And pi radians in terms of degrees is going to be 180. I don't know if you remember talking about the circle. Whenever we're completing the circle, right? That pretty much makes 360 degrees, which is equivalent to 2 pi radians. All right, 2 pi radians. Oscillations in waves is almost like completing an entire circle revolution. You understand? Going around the circle one time. So that is the reason why we say that one wavelength has a phase difference of 2 pi radians. If you're completing half a wavelength, then you're going to have a phase difference of pi radians, which means that this is where you would have stopped essentially, right here, right? So that is what we're saying here. This would be half a wavelength. Now, from starting point to the peak, that would have a phase difference of a half, a half, half of pi, half of pi. But that means though that we have quarter of a wavelength. So at quarter of a wavelength, the phase difference is, so at quarter of a wavelength, there is a phase difference. There's a phase difference of pi, half a pi radians. And a half a pi radian is equivalent to 90 degrees. All right. Now, for half a wavelength, we say that it has a phase difference of pi radians, which is equivalent to 180 degrees. But when we have one wavelength now, one wavelength is going to be 2 pi radians, which is 360 degrees. Following? Now, we could also have something else now, because we can continue now. So up to this point now, if we continue up to this point, then it means now that we're going to have 1.25 wavelength. And that will translate to being, pretty much 2.5 pi radians in terms of the phase difference. But this can also mean 3 pi divided by 2. We can put it in mixed fractions. Improper fractions, right? And it continues like that. So it's just something that we must understand, right? And it says what we mean by a phase. A phase is the position of a certain point on a wave, right? And the units can either be in radians, right? It can either be in degrees, or it can either be in terms of a fraction of a cycle, right? So those are some things that we ought to pay attention to. And as you can see here, this diagram kind of sort of explain it or break it down a little bit more in terms of its, I think I had probably made a little bit of mistake right here. When it comes down to 1.25, 1.25 wavelength will be more than this. All right, so yeah, that it will be more than this. It wouldn't be this, because when I look at the diagram there, I realize now that it will be more than that. This is going to be 5 pi upon 2, which is going to be 5 multiplied by 360, not 360 but 180, my bad. 5 multiplied by 180, because what pi means, pi in terms of radians means 180. So we're saying 5 times 180 divided by 2. We could go ahead and say, all right, 2 into 180 goes 90. So 5 times 90, that's going to give you 450 degrees. So at this point, we would have 450 degrees at that position, right? So that's essentially what is taking place there. Now, just a little bit more in terms of, when we talk about something being in phase and out of phase, because those are some terminologies that you will hear us talking about. Because from time to time, you're going to see more than one wave, progressing as we move from one point to the next point. And so for that reason, you will hear us talking about when something is in phase and when something is out of phase. All right? And that has to do with the position where the waves are located at. So as you can see here, I am starting a wave at this position, right? And there's another wave that is starting further behind of this one, because this one is going to start before the one that is at B. So what you will see is that one wave is going to lag behind the other. So A is starting, but the amount that it lags behind, we can find the amount that it lags behind. So when we look here, we're traveling with this wave. So it's almost like somebody running a race, right? And the one at position A would have started before the one at position B. You want to know how much the one at A is in front of the one at B. So what you would do is to find out where exactly, A is at, or in a sense, how can I say it? So you want to see where, on your wave, on the wave A, where B starts basically. And from there, so you will see how much A is leading by. So when we do this, we realize that this is where B starts. And if we extrapolate and go all the way up right here, then we would see that A is leading, or you would say A is leading by amount of, this would be quarter of a wavelength. This would be quarter of a wavelength, right? Quarter of a wavelength. And quarter of a wavelength is really equivalent to 90 degrees. Let's look back at it. I'm going to look back at it and see. Let me see. I think it's 90 degrees. 1 second. Yes. So quarter of a wavelength would be 90 degrees. That's what I'm saying. Or in other case, we could say that the wave is lagging by a half of pi radians. A half of pi radians, because remember now, one wavelength, or one complete wavelength from A here to all this point here, that would be 2 pi radians. Now here would be your half of a wavelength, which would be pi. So at position B, right, we're seeing that A is leading by pi divided by 2, which is equivalent to 90 degrees. So that's the amount that is leading by. Okay, so this was supposed to be quarter of a wavelength. My bad. Quarter of a wavelength right here. And that quarter of a wavelength is translating to be 90 degrees, or pi divided by 2 radians. So you will see that it says that the phase shift, which is the same thing as the phase difference, is equal to 90 degrees. And it tells us that A is ahead of B, right? So it's telling us that A leads B by 90 degrees, or by quarter of a wavelength. Now, when we consider this one now, B is starting before A. But when you look at where A is starting, it is starting when B is at this position, which is pretty much quarter of a wavelength, which is the same thing as to say pi divided by 2 radians. So in this case, we're still now, B is now leading by 90 degrees, or we could say pi upon 2 radians. You could also say that A is lagging by pi upon 2 radians, or 90 degrees. Now, what if now we start at the same position, however, right, they are going in complete opposite direction. If the waves are going in complete opposite direction, then it means that the waves are out of phase. By the way, these waves right here, right, they are out of phase with each other. They are out of phase. This one and this one, out of phase, because they are starting at different positions, so to speak. Let me see. Yes, they're essentially starting at different positions, right? So if they even ask you how much the wave is out of phase by, the same thing would be the same thing as the phase shift. So if they ask you how much is the phase out of phase by, then it means that it is talking about how much one wave is leading or lagging behind each other, which would be the same thing as saying pi upon 2 radians or 90 degrees. So because these points essentially don't start at the same point, they are out of phase with each other. If they're not moving in the same direction, they're still out of phase with each other, right? So let's look at this now. We'll soon talk about what it means by in phase. So these two right here, they're starting at the same position, but they're not going in the same direction. So they're out of phase, right? These two, while they are starting in the same position as in the positive region, they are out of phase because one is lagging behind each other. So there are two things it means when something is out of phase. One, it means that they are starting at different positions, right? And that they have a phase, they have a phase shift of certain amount, right? What if now we consider the wave, one going starting in the positive portion here and another starting in the negative portion. In this regard, we can say that the waves are completely out of phase. They are completely out of phase, and we're going to see what we mean by that. So we're saying that they're completely out of phase. So with this scenario here, right, A and B is completely out of phase with each other. Completely out of phase, right? And when something is completely out of phase, it has a phase shift of 180 degrees, or we say pi radians, right? So in a sense, A, even though they start at the same position, A is essentially, we could say that A is leading by 180 degrees. We could even say B is leading by 180 degrees. But in this case, because they're going opposite direction, right? And, you know, when we check it out right here, this is where they meet back. The point where they meet, that translates to being pi radians, which is pretty much half of a wavelength. So because they are meeting at this point, then we use that to say that that's the amount that they're out of phase by. All right. But suppose now we start both A and B at the same position, right? Suppose we start A and B at the same position and going in the same direction by the same amount. Let me see here. Yeah. So if you look right here, it says A and B waveforms are in perfect step with each other, which means that they don't have a phase difference because they start at the same position. So A is going like this, right? And then now I'm going to use a different color for B. So B would be on the same wave, as A. So with that being said, we now say that these two waves are completely in phase with each other. Mind you, they don't have to have the same value in terms of the size of the wave, because one could be bigger, but from the mere fact that they are, you know, cutting across each other, because if you compare this, right, this would mean in phase. This would mean in phase with each other, right? And by meaning being in phase, it means that, you know, that they will essentially have, what would we say here? They would essentially have, you know, a phase shift of 0 because none of them is lagging behind each other. So phase difference has to do with the amount that it lags behind each other. Phase shift would basically mean the same thing as phase difference. So because none of them is lagging behind each other, then we say that they are in phase, and in this regard, it's completely in phase. Now, once there's a lagging effort, then it means that they're out of phase. All right. So the best way to find out how much they are out of phase by is to see how much or where exactly is this wave corresponding to this wave on the graph, right? So once you can see that clearly, to say that, all right, this is where my half or quarter wavelength is. What happens when I'm seeing quarter wavelength on the x-axis? How much is that being out of phase by, right? So that speaks to that. Another thing that we can speak about is the fact that whenever we have one particular wave, right, such as this, like we're just considering one wave and we have different points on that wave. We can also have in phase scenario on one wave by itself. So if we look at this position B, is in phase with position G because it have the same displacement. Right? A, E, and F and J, they are all in phase with each other. They are all in phase with each other, right? D and I, they are all in phase with each other. C and H is all in phase with each other. So that's another thing that you must be mindful of, right? They are in phase with each other. Okay? Yeah. Another characteristic of a wave that we must talk about is the fact that there is what we call the speed of the wave, right? Or the speed of the particle. Mainly though the speed of the wave. All right. So one of the things that we must understand is the fact that because the wave is what we call it, oscillating, moving back and forth, right? You can imagine that the wave is going to travel to some distance within a particular time. And for that reason, then we can consider the speed, because if you can measure the distance of the wave and you can measure the time that the wave is traveling, then you can pretty much find the speed of the wave. But an easy way of looking at it is to consider the wave when it is completing one wavelength. And you know that whenever you complete one wavelength, that is when you complete one period. Okay? So for that being said, then we could simply say that the speed of a wave, which we'll use the symbol v, is equal to the wavelength divided by the period. So we could even write it out as this to say, that the velocity is equal to the wavelength divided by the period of oscillation. So if we consider a simple wave right here, right? This would be from here, from this point to this point, would be one wavelength. That would be one wavelength. But at the same time, if I were to take the time from this point to this point, that would be one period. So having said all of that, it's much easier for us to say that the wavelength or the velocity of the wave is equal to the wavelength divided by the period. Now, because we know that wavelength, I mean not wavelength, but period is the inverse of frequency, because because period is the inverse of frequency, we could do this. We could go ahead and do this. We could do several things. We could do several things, but this is what I'm going to do. I'm going to take T and I'm going to substitute it for 1 upon F in this equation. So if I'm substituting T here, then it means that I have V is equal to wavelength divided by 1 upon F. And whenever we're dividing fractions, we can rewrite it as such to say that V is now equal to wavelength times the reciprocal, which is F divided by 1, which now tells me that my speed is equal to the wavelength times the frequency. So this is another equation that you will come across to say that wavelength is equal to frequency. My bad. Speed of the wave is equal to wavelength times the frequency. And this is just a proof to just show you what we're doing because of the relationship between period and frequency. You just have a simple question here. It says that an observer noticed that, right, a boat passes a 4-meter long stationary boat. So a wave passes a 4-meter long stationary boat. It says one crest touches the front and the next touches the back at the same time. So let's look at a boat. Imagine that we have a boat right here. This is our boat. What he's saying now is that one crest I'm trying to see if I drew this correctly. Let me just draw the wave first. Let me just draw the wave by itself first. So this is our wave oscillating like this. Alright, I'm drawing my axis like this. That's my 0 point. Now I'm going to draw the boat. So here's the boat. The boat is essentially like this. What this tells us is that we know that for one wavelength is the distance from one crest to another crest. If the boat has a length of 4 meters, it means that one wavelength from crest to crest is going to be 4 meters. All right. Now the question goes on to say that if 10 crests passes the front of the boat in 20 seconds, it says estimate the speed of the boat. So we know that the number of oscillations, right, is going to be 10 oscillations. Number of oscillations is equal to 10. And the time that it takes to complete those 10 oscillations is equal to 20 seconds. We could simply find out several things here, right? We could find out the frequency, right? Or we could also find out the period. We know period is equal to the time taken, right, divided by n. Time taken is 20 seconds divided by the number of oscillations. This tells us that our time period is going to be 2 seconds. So to complete one wave cycle, right, that would be 2 seconds. Similarly, because we know that, frequency, because we know that frequency is the inverse of period, we could have gone ahead to say that 1 divided by 2, right, is going to give us 0.5 hertz. So we could simply know, now that we know the wavelength, which is 4, we know all of this information. We know the period, right? And we know the frequency. We could have gone ahead to say that wavelength, speed, is either equal to wavelength divided by period, or we could have said speed is equal to wavelength times frequency. Either way we take it, we'll still get the same answer. So if I say 4 divided by 2 is going to equal to 2 meters per second, right? And if I go ahead and say, V is equal to 4 times 0.5, I'll still get the same 2 meters per second. And mind you that when we're talking about speed, it's the same thing to say, meters per second. All right. So with all of that being said, we know we can now move on to another question to just look at some other things. I mean, here we have a tuning fork of frequency 170 hertz produces sound waves of wavelength 2 meters. It says calculate the speed of the wavelength. So we can just simply go ahead and just say, all right, wavelength times frequency. And for that reason, though, we know the wavelength times, 270. 170 rather. We're going to get that the wavelength of the sound that is coming from the tuning fork is going to be 340 meters per second, and there we go. Nothing too hard as yet. Now we move on to different types of waves. So what you have to understand is that there are different types of waves. You would have learned this already at some point, but it becomes more and more important to us. Now, one of the type of waves we're going to talk about, the first one here is what we call transverse waves. And transverse wave is a wave in which the oscillation of the wave takes place at right angle to the direction of the travel of the wave. It is when we shake a rope up and down, the oscillations, right, of all the particles of the rope takes place in the vertical plane, right, as the wave moves forward. So if you look at this, right here we have a wave. These are the particles in the wave. They are moving up and down. They are moving up and down. But at the same time, what you're seeing is that the movement of the wave is going towards the right. So from this, we are now seeing that the oscillation is taking place right angle to the travel of the wave. So that is the important thing about transverse wave, the right angle, because you're moving the thing up and down like this, right? Up and down to produce your transverse wave. But when you look at it now, the wave is now moving in this direction. So this is kind of like what makes it become a transverse wave. All right. One of the things that can happen whenever we have transverse wave is that it can go through a process of what we call polarization. All right. What this simply means is that let's imagine that we were to set up a slit, a vertical slit, which is just like cutting a piece of cardboard. Imagine you have a cardboard and you cut out a vertical piece of slit through it, as in a vertical. Let's cut out a rectangular vertical box. You just cut out that piece as you're seeing here to create what we call a slit. If I were to allow the transverse wave to pass through, obviously it's going to pass through the vertical slit because transverse wave is moving vertically, it's moving up and down. So they're going to pass through. But what if I were now to take another slit and make it becomes a horizontal slit? What you would see is that the horizontal slit is going to block the vertical wave from going through it. So in a sense, when you check it out at the end of the day, it's going to pretty much like kill the wave in a sense. It's going to damp the wave in a sense. So that's what we mean by polarization. Polarization is to uh, literally allow a specific wavelength to pass through a particular state. And we'll look at that further down when we move on. Right? But another thing I must implore to us for us to understand is that whenever a wave is oscillating, the particles are not moving. Because as you can see, this is where the red is located. And when it comes back down, the red is still going to be located there. So the particles are not moving. Whenever we talk about wave, it's a transfer of energy. So always remember that from one point to another point. Another type of wave that we should look at is what we call longitudinal wave. And it says that a longitudinal wave is one in which the oscillation takes place along the same line as the line of travel of the wave in a sense. So what we mean is that you're oscillating the wave, right, in the same direction the wave is going to move. When you look at transverse wave, you oscillate it up and down, but the movement of the wave is going vertically, as in it's going, not vertically, but it's going horizontally, so to speak. When it comes down to longitudinal wave, you're oscillating it in the same direction where it is now going to move at the end of the day. All right. So that's what we look at when it comes down to a longitudinal wave. Now, another thing that we should talk about is that whenever we're dealing with longitudinal waves, that's what we call compression and rarefaction, right? Now, here's what we call a rarefaction. A rarefaction is pretty much that part of the wave that is spreading out. So like right here a while ago, let's look at it. So this would be a compression. That would be a compression that you're seeing going there. But in between the compression, there's what we call a rarefaction, right? So here's the compression, as you can imagine. And with a compression, you're seeing the spring much closer, or the waves much closer. But now, in between that will be the rarefaction. So from one compression to another compression, that would be a wavelength. So that's how you find a wavelength whenever you're looking at a longitudinal wave. Now, one other thing about a longitudinal wave is that it cannot be polarized, right? It cannot be polarized. So, in a sense, it cannot be blocked using a slit. It will always pass through the slit. Okay? That's what we mean. Now, this is what we were talking about polarization. It says that this is the production of a wave oscillating in one plane, that is, with one oscillation or one line of oscillation from a source of randomly oscillating waves. So look at this right here. One other thing you must understand, whenever we talk about light, right? Light is made up of two types of waves. It's made up of an electric field, right? And it is also made up of a magnetic field per se. So as the name suggests, electromagnetic radiation. The light that we see, that visible light, is electromagnetic radiation. Electromagnetic radiation. As you can imagine, the two words right here, electro and magnetic, right? What it tells us is that whenever we are looking at a light wave or light on a whole, right? It is not only one thing that is oscillating. It's not just one wave that is oscillating. There are two waves that is oscillating, and maybe there are more. But for this part, there is an electric field that is oscillating, and there's also a magnetic field that is oscillating. However, when we're looking at it, we see that they are actually at right angles to each other. So one is oscillating like this, right, in another plane, and another is oscillating in another plane. So they are actually at right angles to each other. So when it comes down now to polarizing light, what we're essentially doing is blocking out one of these waves. So as you can imagine, here we have a slit. Here we have a slit right here, and we are taking what we call an unpolarized light. Now, when that unpolarized light hits the slit, depending on the type of slit, if it's a vertical slit, what it means is that it's going to only allow vertical waves to pass through it. So as you can see on the other end, it's the orange wave that is passing through, and that is just because of the fact that it is it's vertical and the slit is vertical. So imagine this is the same thing that's occurring here. If you put a vertical slit in front, then it's only going to allow vertical waves to pass through it. But now, what if I put a second slit in front that is a horizontal slit? Those vertical lines will no longer pass through that slit because of the fact that the slit will not accommodate or allow a vertical to pass through a horizontal slit. So in a sense, it would block out the light. When you now think about certain glasses that we wear, right? When we say that the glasses is polarized, what we really mean is that it is able to block out a particular wavelength of light from our eyes, especially UV rays. Okay, so you will see that from time to time, right? Where not only we soon talk about the glasses, but another application that we should talk about is in photograph. Whenever you're taking photographs using a camera, because sometimes water might be within or in close proximity to where you're taking the photo, right? And for that reason, sometimes a reflection is on the water surface. So to prevent that reflection from interfering with the overall quality of the image, then you use what we call a polarized lens to pretty much block out that type of light that is coming from the reflection. All right. So that's kind of like a way of getting rid of polarized waves in a sense. So you can do a little bit more reading up on that part. When it comes down to the sunlight, as we said, it says a polarized sunshade may use, all right, or make use of polarization in that, they block out one of the two net components of light, reducing the light intensity by 50%. It says that in polarized shade, the plane of polarization is usually vertical, since light reflects off water, for example, beaches is polarized in a horizontal plane. So there are several things that's happening there. You can read it up for yourself, all right? Progressive waves. So another type of thing now that we will talk about. Progressive wave is nothing new in a sense, right? What we have been talking about so far, they are classified as progressive waves. Progressive wave is waves that really just transfer energy from one point to another. So waves on a whole is a progressive wave. And it says without the transferring of materials. All right. As you can imagine, for any wave that we will talk about, there is an equation that satisfies the wave. Now, if you remember anything about circular motion or simple harmonic motion mainly, whenever we start our oscillation from zero, we generally use a sine wave to represent that. And if we're dealing with the displacement versus time graph, then this is the equation that comes in very handy whenever we're trying to find out certain information. There are two types of graphs that we can plot when it comes down to progressive wave. We can plot a displacement versus displacement graph per se, and we can also plot a displacement versus time graph. So your displacement versus x graph, it looks like this, where it says that your displacement x, which is your amplitude, no, not really amplitude, yes, your amplitude or your displacement for argument's sake, right, is equal to the amplitude of the wave times sine of k times x. Now k is what we call the the propagation constant, right? K is what we call the propagation constant. How we find the propagation constant? The propagation constant here is equal to 2 pi divided by our wavelength. All right. So if you want to find the propagation constant, this is what you would use to find the propagation constant. There's another formula that we can also use to find the propagation constant, and that is essentially equal to say that k is equal to omega divided by the wavelength. All right. So that's something you can also use as well to find the propagation constant. Okay. So just remember this equation for a wave. All right. So we know already that omega, which is your angular frequency, is equal to 2 pi divided by t, or we could say 2 pi times f. All right. So just remember those information as it pertains to progressive waves or waves in general. So as we said, this is the overall equation. This just ties in everything that happens here, right? This just ties in everything that happens, right? It just ties in everything. As we said, that A is the amplitude, right? K is our propagation constant. Omega is your angular frequency. X is just your displacement, which is just a position where the wave is located at the time. Yeah. Another feature of a wave that we should talk about is the intensity of a wave, right? So as you can imagine, the more or the larger the amplitude of the wave is, right? It's the more intense we say the wave is, right? Or in some cases we can say the more power the wave also has, it has more power, more energy if you have a very high amplitude. So it says that one of the characteristics of a progressive wave is that it carries energy. It says that the amount of energy passing through, unit area per unit time is called the intensity of the wave. So we must know the defined intensity, right? So it's just that the amount of energy that is passing through, a particular area, right, per unit time is what we call our intensity. But we can do this now. So intensity is essentially equal to, right? Is essentially equal to energy, right, divided by area times time. But we know that energy divided by time is equal to power. So for argument's sake, we could also say that intensity of a wave is the power per unit area. So if you want to find the intensity, you need to know the power divided by the area. So that's what it really means. So now intensity, as you can see here, at some point you're going to see that intensity is proportional to the square of the amplitude of the wave. So what it tells us is that if we double the amplitude of the wave, the intensity is going to increase by a factor of 4, right? So that's just simply what we mean here. So from time to time, you'll see that the intensity, right, is because of the fact that there is a directly proportional relationship, I is going to be equal to K times A squared, which just tells us that our intensity is directly proportional to the square of the amplitude of the wave. So if I increase my amplitude, right, by a certain amount, then my intensity is also going to increase by that factor. All right. Another type of waves that you'll hear us talking about is what we call standing waves, right? And with standing waves, you can also hear we talking about stationary waves. It's the same thing as standing waves, all right? So that's something that you should pay attention to. So if you see the terminology stationary wave, it's the same thing as standing wave. While the wave is not completely stationary, right? There's a little bit of movement in it. But the beautiful thing about stationary waves or standing waves is that the energy is not transferred, but it's rather confined to a set distance. Meaning, so here's the wave progressing, up and down. Then it meets a barrier. That barrier, what it's going to do is going to reflect the wave. And by reflecting the wave, it's going to now oscillate in the opposite direction. It's going to oscillate in the opposite direction. Right? As you can see here, this is a standing wave on a string. So what we're literally seeing here is that when the string meets a barrier or a boundary, it's going to reflect in the opposite direction. And in that process, it produces what we call a standing wave. Now, as you can see, you're seeing like, some loops being formed here. We're going to talk about those things because those things are critical to us. And we're going to use that in understanding certain things. Now it says that there are, these waves rather, have points which do not oscillate. So there's a point that the wave do not oscillate. So like right here, right at this point is when the wave don't oscillate. We call that a node. So that's what we call a node, the point where no oscillation is taking place. Now it says points where oscillation are points which oscillate rather with maximum amplitude, right? That is what we call an antinode. So right here is going to be an antinode. And that is just the point where the maximum oscillation occurs. Pretty much talking about your amplitude, so to speak. All right? One of the things you must understand is that halfway between a node, you'll find an antinode. Then clearly you're seeing another node right here. So another node occurs here. So halfway in between two nodes would give you, right, an antinode. All right? So those are some of the things that we must be mindful of. And we're going to look at it in greater depth in the next slide. But it says that a loop appears to be formed between successive nodes, right, as the wave travels back and forth rapidly, right? The reason why we're not seeing the loops being produced here is because this is not vibrating rapidly. But because this is now moving very fast and vibrating very quickly, it appears to be that there are loops, that a loop is being formed. But in essence, this is what it looks like. There's not a loop that is being formed in real life. But because it's vibrating so fast, it appears to show, or it appears to the eye, that there's a loop that is being formed. But it's not a loop. It's just based on how the thing is reflecting back and forth. Now, stationary waves and standing waves as we know it, we can find the wavelength using the length of the string. So as you can imagine, in most cases, when we're talking about standing waves, we're using a string to produce standing waves, right? So imagine that here's a barrier. So this is one barrier where a node is going to be located, right? And then here's another boundary, another barrier, where you'd find another node. One of the things that we must understand is that from node to node, right, from one node to another node, that's going to be recorded as a half wavelength. And it's the same thing. If we consider a typical wave that is starting here All right, let me just redraw that. Right? So we know that half of a wavelength is when we have one, you know, one crest, so to speak. I guess that's what we mean. Let me show you what I mean right here. So let's imagine. So half a wavelength would be from here to here. So we're looking at this thing right here, right? This standing wave between two nodes. You're seeing half of a wavelength. Half of a wavelength. From here to here is another half of a wavelength, which means now that you would have one complete wavelength. So whenever you see one loop by itself, that is half of a wavelength. From a node to an antinode, that's going to be quarter of a wavelength. All right, so that's something that you must remember. You must remember that information pertaining to the wavelength and where, yeah. So another thing that we must talk about, right? So somewhere in your books you can write this to say that, from an antinode to a node, that is going to be quarter of a wavelength. The idea here, guys, is that we want to determine the wavelength of this particular wave. In order for us to do that, we have to consider the length of the string. What we're saying here at this point is that the length of the string is equal to half a wavelength. The entire length of the string is equal to half a wavelength. So half a wavelength is equal to the length of the string, which we're going to record it as N. Not N, but L rather. L. So for me to find my wavelength when I have node to node, all I would do here is to just transpose for wavelength. So wavelength is going to become 2L. So what that tells me is that for me to have a complete wavelength, right, this length of the string must be doubled in order for me to get the entire length of the, or to get the entire wavelength of the wave that is being formed, right? So that's how we basically find the wavelength using the knowledge that we have here. There are other ways we can do it. Which I'm going to talk about very soon. Now, whenever we have what we call a closed-end standing wave, a closed-end standing wave is when you have two nodes. When you have two nodes on both ends, that's a closed-end standing wave. Imagine that you have one, closed-end standing wave, meaning that you have one end closed here and another end closed here. We could call it two closed-end standing waves. As we can see, if that's the case, we can say that this is at the first harmonic, right? Whenever we're seeing one complete loop, right, between a closed end, we say that this is the first harmonic. And by us saying that, it means that n is equal to 1, which here n speaks to the number of antinodes in this regard. So based on the number of antinodes that we can count, visibly count, between the closed ends, then that will now tell us the number of harmonics. All right. Now, with all of that being said, we could come up with a formula. We could essentially come up with a formula that we could use to find the wavelength when n is equal to a particular number. So, for me to find the wavelength of a string, right? When n is equal to 1, then I would say wavelength when n is equal to 1 is equal to 2L divided by n. In this case, because we said when n is equal to 1, then it means that 1 would be in the denominator. So at the end of the day, when n is equal to 1, the wavelength is equal to 2L. When n is equal to 2, so if n is equal to 2, then it means that the wavelength is now equal to 2L divided by 2, which is going to say that lambda is equal to L. Alright? In just the same way, we can come up with a formula for the wavelength. We can also come up with one for the frequency. Right? So, for us to find the frequency, we can still use the same harmonic mode, right? So if I want to find the frequency of this particular wave, and this particular wave has n equal 1, then all I would do is put the 1 right here and times that by the frequency. But we could also write it as such. Because we know that frequency and wavelength has a relationship. Because frequency and wavelength have a relationship, and that relationship comes by when we're talking about the speed of the wave. The speed of the wave is equal to wavelength times frequency, right? So we could come up with another formula when n is equal to 1. When n is equal to 1, lambda is equal to 2L, right? So if I substitute lambda in this regard, I would get that, speed is equal to 2L times the frequency. And for that reason now, and this, by the way, this is when frequency is equal to, when n is equal to 1, so f is going to equal, so frequency is going to be f1, so to speak. If I transpose for frequency, I now see that frequency for the first harmonic is going to equal to the speed of the wave divided by 2L. You understand? And this is just because f is equal to 1, right? That is just the reason. If f was equal to 2, then we would have to do a lot more other stuff. You understand? But yeah, we're going to do some more practice as it relates to standing waves. Here's another example. If I have two antinodes, so here's one antinode. This is two antinodes. So it therefore means that n is equal to 2, right? So in this regard, we are using the equation that says lambda n is equal to 2L divided by n. As I would have shown you earlier on, if n is equal to 2, then it means that 2 times L divided by 2 is going to equal to L. And of course, for us to consider the frequency, right, then obviously we would have to use that same formula that says Fn is equal to n times F1. You understand? Since n is equal to 2, then F2 is now going to equal to V divided by 2L times 2. You understand? And so we can see that the 2 would cancel out, leaving us now to say that the frequency of this wave would be the speed divided by L, by the length of the string. So L is the length of the string. Comprende? And we could continue this with several other things, to find out when n is equal to 3, what would be the wavelength, all of that kind of thing. But I want to show you, what if you don't remember this formula, which you should remember the formula. You have to remember the formula. Then you could find out the number of wavelengths by counting this, right? You could find out the number of wavelengths by counting the um, number of wavelengths that are here. So let's imagine that, you know, this is obviously going to be um, a quarter of a wavelength, and this is another quarter of a wavelength, and this is another quarter of a wavelength, and this is another quarter of a wavelength. So in essence, right, by counting up all of these, then you would see that at this portion of the wave, that's when you would have one complete wavelength, right, which is going to be equal to 2/3 of the length of the string. So this entire wavelength here is equal to 2/3 of the entire length of the string, as you can see, 2/3 of the entire length of the string. Now let's just consider this question. It says that the vibrating length of a guitar string is 90 centimeters. It says if the string is sounding a frequency of 256 hertz, right, in the first harmonic, which is the first loop, it says determine the speed of the sound on the string. So clearly we have a guitar that is creating a standing wave, right? When you play a guitar, if you play a guitar, in essence, you're actually using the whole concept of standing waves to produce the sound, because further on in physics you'll find out what we mean by that. So this is just my guitar for argument's sake. I don't know how to draw a guitar, but this is just my guitar, and I have created one complete you know loop, right? And we're saying here that the length of the string is 90 centimeters, which should be converted into meters as 0.9 meters. So that's the entire length of the string. Because n is equal to 1, then by using the equation that says wavelength when n is equal to 1 is equal to 2L divided by 1, because n would have been equal to 1. So it means now that the wavelength is equal to 2 times 0.9 meters, right? Which is going to give us to say that the wavelength of that sound wave is going to be 1.8 meters. Having said that, it wants us now to find the speed. We know that speed of a sound wave is equal to wavelength times the frequency. We have the frequency for the first harmonic. We have the wavelength of the first harmonic, so we have 1.8 meters times 256, right? So when we do all of that multiplication, we now get an answer of 460 meters per second, right? So that's typically what we are doing here, all right? Nothing too complicated as yet. This is probably where it will get a little bit complicated, right? But you know, so another thing that we must understand is that standing waves, you see, we can generally form standing waves in an ear column. And what we mean by an ear column, it's just like an empty tube. So if you consider certain musical instruments, right, like a flute and all of that, they make use of standing waves to produce the sound, right? So what you're seeing happening here is that if you were to blow a sound inside of this, ear column, you would basically be forming standing waves, providing that the end is closed right here. So you have different types of ear columns. You have a closed end and open end ear column, right? And you have ear columns that have both open ends and all of that. It can become a little bit tricky when you want to find the wavelength of the sound wave using this scenario, right? But what I want you to understand is that because you have a closed end at this point, it means that this is where your antinode would be located. Not your antinode, but your node Your node will be located at this point. At the open end, you will have your antinode. So at the open end, you will have your antinode, right? Now let's consider when n is equal to 2 in this case. When n is equal to 2, your antinode is here. Not antinode, your node rather is here, right? Here is another, here's your first antinode. And then now here would be your second antinode. Right? Your antinode is just that point where you're seeing the maximum displacement. So that is when n is equal to 1 in this case. All right? Yeah. These are some other examples of what is taking place within, an ear column, right? As I said, you can have both ends open for an ear column. This would be how it looks when you have the first harmonic. Clearly, you would have an antinode here at the open end, and clearly you would have another antinode here at the open end. Similarly, if you were to look at the closed end, you would have an antinode, a node right here, and you would have an antinode at this point. Similar thing that it goes right on just along the same, it continues, right? So that's just a view of what is taking place here and all of that. Now, in certain experiments, we are in a lab, we can actually try to measure the wavelength of a standing wave using the whole concept of the ear column scenario, right? So imagine that you said, when a sound source of frequency 256 hertz is placed at the open end of a uniform tube containing water, the first two loud sounds are heard when the length of the ear columns are 0.3 meters and 0.098 meters respectively. It says determine the speed of the sound in the ear column. All right. So one of the things that I must point out to you is that there's a concept by the terminology of resonance, right? I'll speak more about it further on. But what you would observe is that if you were to fill this container with water, right? Imagine that the water is at this level. You understand? And then you allow the water, as a matter of fact, let's pull it up to the brim, as in to this capacity. And then you allow the water to run out of the container. When it reaches this point, what you're going to observe is that you're going to hear a very high-pitched sound. What the high-pitched sound signifies is that there is what we call resonance taking place. And resonance takes place when the frequency of the sound, in this case, matches the natural frequency of the particles inside of the ear column, right? That is what resonance really is talking about. So for us to understand, or for us to measure the wavelength of sound waves, right? What you would do is that you would allow water to be in a column like this. Then you would slowly let out the water, providing that you have a source that is providing a consistent frequency of sound. Now, as the water is running out, what you would observe is that at some location in the tube, an antinode will be formed. And the antinode just signifies that resonance is taking place, which means that the sound wave, the frequency of the sound wave is now matching or now equal to the frequency of the particles that is vibrating inside of the ear column. So it will happen at several locations. So at the first location, they said that it occurs when, there was a measurement of 0.3 meters. Then the second one would have occurred right at this point, where you have, a length of 0.98 meters. So at this point, what we want now, we want to find out what the wavelength is. You understand? We essentially want to find out what the wavelength is. Now, to prevent an error, in this experiment, we will not consider the distance between the first antinode. We will not consider the distance between the first antinode. The reason for that is because of the fact that at this open end, there will be an error, what we call an end error. The end error comes as a result of the fact that it does not completely tells us that we're at a complete antinode, right? So that's the reason why we don't want to use that information. Because we could have used that information as to say that quarter of a wavelength is equal to 0.3 meters, but we don't want to say that. Because if we do say that, we run the risk of having an error. Because as you can see at the open end, it means that the antinode could have been much higher. Maybe at this point, it could have been a little bit lower, all of that kind of thing. So we don't want to run the risk of that. So what we do now is that we're going to consider the second, portion of the wave, right? Because what you have to understand is that from here, from 0.3 meters to 0.9 on this portion here, right? In between here, you will basically have half of a wavelength. And so we can say that half of a wavelength is equal to the difference between the 0.3 and the 0.98. So when we do subtract this, we're getting that half of a wavelength is essentially equal to 0.68 meters. Having said all of that, we can transpose to find the wavelength. So all we're doing now is say that wavelength is equal to 2 times 0.68 meters, which is now telling us that the wavelength of this wave is going to be 1.36 meters. Having said all of this, right, we can now find out the speed. Speed is equal to frequency times wavelength. So my frequency is 256 times the wavelength I we just calculated a while ago, which is 1.36. We could see that the sound wave would be of a value of about 350 meters per second, right? So from the mere fact you know the length of the standing wave, right, in the ear column, then you can equate that to the amount of the wavelength that is recorded at that point. And from there, so we could, we could essentially find out what the wavelength is. All right. Wonderful. So let's see here. Here's a particular question, right? This is a general. It's a standing wave question mainly, right? So it says that when a note on a piano, right, is played, it says that the sound it produces consists of the fundamentals of many overtones. Now it says that figure 1 shows the shape of the string of a standing wave that corresponds to one of these overtones. It says here that the position of the maximum and zero displacement of one overtone is are shown rather. It says point A and B are fixed. Point X, Y, and Z are points on the string, right? Now the question then goes to ask us. It says state the phase relationship between X and Y. So here is X and here is Y, right? So I believe in this regard, we can simply say that they are out of phase. They are out of phase because they are not on the same displacement, right? They're out of phase. We could also almost consider, let's look at it. We could say, all right, from here to here, right? Or from here to here, that would be pi, right? That would be pi, right? So between here now, this is going to be half of pi, half of pi. So at this point would be at least, I mean, let's consider here. This is going to be at least 3/4, I believe, 3/4 of pi. Okay, and then now let's consider up to this point. This point here is um this is going to be another. All right, so if this is pi, then this is going to be we know definitely that this is going to be 2 pi. That is 2 pi. Good. So this is going to be 1.5. It's going to be 3 upon 2 pi. It's going to be 3 upon 2 pi. What we're essentially trying to do, you see, is to see how much both points are lagging behind each other, right? We're just looking at that. We're just looking at that. So from here to here is 3/4. 3/4. From here to here is 3/4. From here to here is another 3/4. So we're plusing another 3/4. Another 3/4. Then we're plusing another 3/4. So far, you know, um, you know, if we were to add up these, right, from here to here would be a half a wavelength, right? I mean half of pi plus 3 upon 4 pi, right? So we could add up these together to see how much the wave is out of phase by, right? It goes to another point to ask us as well, um, if x, yeah, state the relationship between you know, x and z. Those two, they are going to be in phase. They're going to be in phase, right? But it's hard to determine how much they're in phase by. So we're just going to write that they're in phase. In phase. All right. Now the question then continues to say that the frequency of this overtone is 780 hertz. It says show that the speed of the progressive wave on the string is about 125 meters per second. So that's something that we need to do right now, or So with this question, I believe something got chopped off per se. So I'm going to just finish it off by just adding the final node. So here's the final node. So now for us to find out what's going on here, we need to count the number of antinodes. So 2, 1, 2, 3, 4. There are 4 antinodes, which means that is equal to n is equal to 4. Now L, as you can see from the diagram, is going to be 320 millimeters, which we're going to say times 10 to the minus 3 meters. Then from there, we could find the wavelength. The wavelength when n is equal to 4 is equal to 2 divided by L, right? Times times 4. So we could go ahead and see what's going to happen now. So 2 times L, which is 320 times 10 to the minus 3. Divide that by 4. All right, so 2 into 4 goes 2 times, 2 into 2 goes 1 times. So let's see what we have now. We have 320 e to the minus 3 divided by 2. When we do that, I'm getting 0.16 meters. So that's my wavelength when n is equal to 4. Having said that, we know that speed is equal to wavelength times frequency. Frequency is 780 times my wavelength 0.16. So when we go ahead and multiply that, we're getting a value to say that our speed is going to be 124.8, and of course this is translating to be 125 meters per second. Okay, so that's a really nice question there that just incorporate most of what we have learned so far. So this is the end of this lesson, and we will resume by then talking about reflection, right, and so forth in the subsequent lesson. All right, so stay blessed.